What?
The replenishment for the oxygen.
No, the electrons are the replenishment for the electrons that were moved around and shuffled this direction. Jimmy, how many products were there from the breakdown of water? 3. And I've taken care of where the O2 goes. I've basically told you that I had to break down water to replenish the electrons. And so there were 3 products, and so I still have to talk about the H, right? The H+, which is a proton, the hydrogen ion. Now, you could imagine very quickly that if one electron gets excited, there's nothing stopping you from exciting 2 and 3 and so on and so forth to a great number, correct? So definitely the number of electrons that end up over here would start to accumulate very quickly. And if you think about it, for every number of electrons that have to end up over here, you would have to break down water molecules. So over the course of time, what would happen to the H+ concentration within this Psi liquid? It would start to go up, right? Because you'd have to break down more water to fulfill the electrons. So I think the amount of H+ could start to become quite staggering inside this area. Let's talk real quickly about this buildup of H+. H+ buildup causes an acidic environment. But not only does it cause an acidic environment, it creates a gradient. Do you know what type of gradient this is right there? That is the second time that we've discussed the idea of an electrochemical gradient. We discussed it last week. We discussed it now just today. How do you solve the H+ electrochemical gradient? We solved it one way last week. I'll tell you, we'll solve it the same way today. What was that way last week? Where did the H+'s go through? What was their doorway? An enzyme called ATP synthase. So, I'm going to draw out the ATP synthase molecule again. That's called ATP synthase. And just to kind of guess or estimate, ATP synthase, what do you think it's going to be making? Okay. So this electrochemical gradient and all of its H+'s that are in that gradient are going to flow down their concentration or electrochemical gradient to this area to the outside, and every time they do, you'll generate some ATP. And you do so from the ADP plus the inorganic phosphate. So a couple questions about this process. Is the production of ATP endergonic or exergonic? Endergonic. Making ATP is endergonic. So my question to you is, where does the energy to power this endergonic ATP synthesis come from? Ultimately, it comes from light, but what about directly? The H+ gradient, right? That gradient and the movement of particles down it cause the gradient, if you think about it, and that diffusion of H+ has caused the ATP to be synthesized. Now, this morning, one of your classmates kind of said, well, I don't quite get how that gradient could produce energy. So let me give you an example. What kind of cologne is popular these days? Or perfume, or what are y'all wearing? Justin Bieber. Okay, this will probably get edited on YouTube, but let's just say that there's the Justin Bieber cologne, right? And let's say that you're in the back of the lab right over there, and you put Justin Bieber cologne. Let's say you pour out 1 milliliter of Justin Bieber cologne. Will that odor, or that smell, good or bad, will it stay in that area of the room?
No.
Where will it go? It will go and spread, right? In chemistry, there was a D word that described this movement of gas particles. Diffusion. Can you stop that diffusion process from happening? It's just going to happen, right? That means that, well, in short, particles go to where they are not. Things go down their concentration gradient. And as they do so, they expend some energy. As this goes through its concentration gradient, it expends some energy. That energy is locked up in the formation of forming ATP. Good? Now, as more H+ flows through, what's going to happen to more ATP? I think more ATP would be made, correct? I think a problem could exist, though. I think you could reach a point where the H+ has equilibrium on both sides. I need to be taking away some of this H+, correct? As I remove every H+, I'm just going to give need to go down the concentration and gradient more, which is going to generate more what? ATP. So in other words, I need something that is sucking up or removing or neutralizing this H+. And let me give you the other part of the story. This H is what charge? And positive things are attracted to things that are.
Negative.
Where's my negative charge at this drawing right now? Right there, right? So I don't just bet, I actually would guarantee that these H pluses would go on up here. Now I told you that this blue mass up top where my electrons and hydrogens go was an enzyme. Here's the name of it. NADP reductase. What do you think this enzyme is doing? This is kind of a no-brainer, so don't overthink it. Reducing NADP, just as its name implies. So if you take NADP plus, and if you add electrons and hydrogens to it, you are reducing it to form NADPH. And if that's a reductive process, this, in layman's terms, does reduction, does that mean to charge or to deplete? To charge. So you're charging up your NADP plus to NADPH. Now I told you, and this is now the fourth time today, that there were two items that the light reactions are making for the Calvin cycle. What are those two things? I made them both. Questions or comments?